OSHA Part 1910.269 now requires companies involved in electric power generation, transmission, and distribution to inspect and test their liveline tools. In particular, the test must verify the tool's integrity along its entire working length under wet conditions. The test shall be 75 kV per foot for 1 minute or equivalent. No specific accept/reject values are given. The standard does reference IEEE 978, which recommends a stable or decreasing reading as acceptable. Hastings Fiber Glass Products responded to this new industry rule by producing a portable tester that will allow the user to comply with the requirements of OSHA without the expense of full-scale laboratory test. A full discussion of the correlation between this tester and the OSHA rules will follow later in this video. The controls are simple, well labeled, and will allow the user to operate the unit with one hand. The power switch energizes the amplifier and the high voltage transformer. If the switch is moved to the on or center position, the power light will illuminate, the amplifier will be on, but the high voltage will not be present. This is evident by the overload light being illuminated. Moving the switch to the next momentary position will activate the high voltage transformer. Now high voltage is present at the electrodes. The tester allows the user to select between two test modes. Both the wet test required by OSHA and a more sensitive dry test can be selected. The full-scale deflection for the dry scale is 40 microamps. The full-scale deflection for the wet scale is 200 microamps. After turning the unit on and selecting the desired scale, the meter must be zeroed to compensate for leakage due to varying ambient conditions such as humidity and temperature. The unit supplies high voltage to the electrodes on the left and measures the return current through the electrodes on the right. In order to provide worker protection, the current supplied to the high voltage electrodes is limited by two resistors. The resistors are in series with the high voltage transformer leads. Either resistor is capable of withstanding the full voltage and limit the current to a safe level if necessary. Additionally, the amplifier monitors the total current flowing through the circuit and will disconnect the high voltage source should the total current exceed normal test levels. The electrodes are spaced to test 6 inches of fiberglass at a time. To verify the tester is operating properly, a test bar is included. This is not for use in calibrating the unit, only for verifying that the unit is operating properly. When the dry scale is selected and zeroed, a full-scale reading should result when the test bar is inserted. When the wet scale is selected, an indication of between 25 and 50 microamps will result. The dry test is not required by OSHA. It can be used as a tool in determining the integrity of the fiberglass prior to wetting the surface. It is possible for a tool to be cracked or deeply scratched and hold moisture for long periods of time. Internal contaminations on hollow tools can also hold moisture that can be detected with the dry scale. Our recommended acceptance value is 15 microamps. Seldom will a visual inspection of a dry stick yield any useful indication as to its dielectric condition. The stick being tested has been returned from the field. While it looks contaminated, its dielectric value is still quite good. In this instance, we have created a known defect in the center of the stick. Because we use AC voltage, the meter has the ability to see inside the stick without damaging the stick. Because this stick is measuring below 40 microamps, it may pass the OSHA required wet test. Prior to conducting the wet test, there are several important items to remember. First, the water to be used should be distilled. This is readily available and removes the variations in the test due to differences in local tap water quality. When testing hollow sticks, the inside should not be cleaned with a wet type cleaner just prior to testing. Evaporation is poor on the inside of the tube, and it can take an extended time for the moisture from the cleaner to evaporate. This will delay the testing of the stick by several hours or even days depending on the local temperature and humidity. The tool being tested should be wetted until the water just starts dripping. Set the tester for the wet test and zero the meter. Place the tester on the stick and observe the meter. Lift the tester, move down the stick, and take a second reading. Repeat this process until the entire stick is tested. For the most critical results, the stick should be rotated 180 degrees and checked again. While the tester will sense a defect on the opposite side of the tool, the maximum reading can only be obtained by rotating the tool. In this case, the tool measures approximately 20 microamps and passes the test. We will repeat the test on a second tool. The surface shows more damage and contamination than the last. However, visual inspection is inadequate to determine how the tool will perform during the wet test. As the stick is wetted, you will note that the water doesn't bead as much as the first stick. Placing the tester on the tool, we will note that not only does the tool fail the test, but the meter is going off scale. Surface contamination, surface conditions, cracked fiberglass, gouges, and deep scratches can cause a tool to fail the wet test. Most of these defects can be addressed with proper cleaning. Selection of an approved cleaner for cleaning fiberglass surfaces is important. The cleaner must be safe for use and leave no conductive residue after use. For cleaning this fiberglass tube, we are using Hastings Fiber Glass Products all-purpose cleaner, which is recommended for all fiberglass surfaces. It leaves no residue and is completely safe for use. Ultrafine cleaning pads are extremely helpful in cleaning areas that have dirt and contamination deeply embedded in the surface. After cleaning the surface of the fiberglass stick to be retested, you must ensure the fiberglass is completely dry. Hastings Fiber Glass Products recommends an application of fiberglass wax on the hot stick surface after cleaning and drying. Use only wax recommended by the manufacturer. It is important to retain a glossy surface as a moisture barrier and to allow the water to bead up on the surface to pass the wet test. As we retest the tool, we observe an obvious change in the reading. While the tool went off scale before cleaning, we are now reading 30 microamps. It is possible to use a silicone wiping cloth to create a moisture barrier, provided the surface condition of the tool does not have nicks and abrasions. The leakage current across the surface of a pole is a function of the applied voltage, length of the test specimen, and electrical properties of the fiberglass being tested. The electrical properties of the fiberglass can be degraded by contamination. This contamination can take many forms. It can be highly conductive particles separated by good dielectric fiberglass, resulting in a higher capacitive current over the surface of the stick. The contamination can also take the form of a more uniform, highly resistive coating, which will result in a resistive current flowing across the stick. It may even be possible to have a somewhat inductive contamination on the fiberglass. In any event, whether the contamination causes a capacitive current, an inductive current, or a resistive current, it will be linear with the voltage applied. Looking at the graph of sample number 1 and number 2, you will notice that the graph of number 2 is more typical of the curves published in the industry. The nonlinearity of the typical high-voltage leakage current graphs are usually the result of the electrodes going into corona and not an indication of the leakage of the fiberglass. This can be demonstrated by changing the electrode design to one which does not produce corona, or examine the part of the curve prior to corona being produced, typically below 75 kV, and you will observe a straight line. This is a result of the familiar equation V equals IR. Knowing that the relationship between the voltage and current on a given sample is linear, we can test at a much reduced voltage with more conveniently sized equipment and determine what the full-scale leakage would have been. This will only hold true when testing samples that are not contaminated to the point that flashover or corona would occur on the stick at full-scale test levels. We will address that in a moment. What we want to establish first is that at the lower levels of contamination, if the voltage is reduced by a factor of 10, the current will be reduced by a factor of 10. If a tool is uniformly contaminated, the leakage current will vary linearly with the length. If the sample is twice as long, the current will be half as much. Or if we test only 6 inches instead of 12 inches, the leakage will be twice as high. If the contamination is not uniform, the smaller the section is that is being tested, the more critical the test becomes. Take, for instance, a 12-inch piece of fiberglass that is highly contaminated over 3 inches. 75% of the fiberglass is still good and will somewhat mask the defect. If, however, the test is performed on a 6-inch sample with the same 3-inch section contaminated, only 50% of the glass is good, resulting in a more critical evaluation. The 6799 uses both a reduced voltage and length. The length between the electrodes is 6 inches and will detect a smaller defect than the 12-inch spacing. The applied voltage is 2500 volts. The scaling factors for the tester are as follows. For the dry test, the readings are referenced to the full-scale values for 100 kV per foot. The 6799 uses a voltage 40 times less than the full-scale test. This means the actual leakage current the tester sees must be amplified by 40 to correct for this voltage difference between the 6799 and the full-scale value. The distance between the electrodes is 1/2 that of the full-scale test. This means that the actual leakage current measured by the 6799 must be divided by 2 to correct for the length between the 6799 and the full-scale values. After both values are amplified, the actual amplification factor is 40 divided by 2, or a multiplication factor of 20. The wet test is similar to the dry test, except that the full-scale value is 75 kV instead of 100 kV. Calculating the same correcting values, we get a correcting factor of 30 for the voltage correction and the same factor of 1/2 for the length, resulting in an actual amplification factor of 15. OSHA doesn't specify a value of leakage current. They do reference an IEEE standard which covers various methods of testing tools. The section in IEEE relating to full-scale, high-voltage testing also doesn't give an accept-reject value. Rather, it states that the reading should be steady or decreasing. Obviously, both standards require by inference that the tool may not flash over. A contaminated tool will flash over if the leakage currents are high enough to cause local heating or tracking on the surface of the tool, or if enough of the tool is shorted such that the remaining section cannot withstand the high voltage stress. In either case, a higher than normal leakage current will be present prior to flashover. Typically, leakage current values much higher than 200 microamps are present prior to flashover. This value will vary with the type and extent of contamination. To set 200 microamps as the accept-reject level would come as close to approximating OSHA requirements as possible. However, there may be situations where an unusually contaminated tool might only measure 180 microamps prior to flashover. Since we are using a reduced voltage and must be sure to always meet or exceed the OSHA requirements, we have to set the pass-fail requirement of leakage current at 75 microamps. For additional information, please contact Hastings Fiber Glass Products.